Okay, ladies and gentlemen, as promised, here is another completely worked out example on how to determine the balanced formula equation, or the balanced molecular equation, the complete ionic equation, and then the net ionic equation. And we are going to work this example from the very beginning. So what I'm going to do is I'm going to actually not even give us the formulas, okay? I'm just going to give us the names of our reactants, and then we're going to just work from there. Okay, so let's say we have solutions of potassium hydroxide and iron 3 nitrate. And we're mixing these together, and we're trying to determine the balanced molecular formula, or the balanced formula equation, whatever it's called, the complete ionic equation, and then the net ionic equation. Okay? Well, the first thing I need to do is I need to determine the formulas of these things, and then I need to predict what the products would be. Okay? So let me go ahead and do the formulas of our reactants first. Potassium is going to have a positive 1 charge due to its position on the periodic table. It's in the first column, so it's got a positive 1 charge. Hydroxide is a polyatomic ion with a negative 1 charge. Okay, so the formula for potassium hydroxide is going to be KOH. 1 potassium, 1 hydroxide. There we go. Okay, so this is my formula for potassium hydroxide. Okay, iron 3 nitrate. Iron is a transition metal. This Roman numeral 3 tells us that the charge is positive 3. Okay? If it was iron 2, then it would be positive 2. Okay? Transition metals need Roman numerals to indicate the charge because they don't follow any particular pattern like the other elements do. Nitrate is a polyatomic ion with the formula NO3, a negative 1 charge. So the formula for iron 3 nitrate is going to be 3 nitrates with 1 iron, right? Remember, we have to have an overall charge of 0 for all of our ionic compounds. So if I have an iron with a positive 3 charge, I must need 3 nitrates, each with a negative 1 charge, to balance out the positive charge from the iron. Okay? So there's my formula for iron 3 nitrate. And this is also aqueous. Okay, now I need to predict the products. Okay, and this is where you sort of have an option. You can swap the cations for each other, or you can swap the anions for each other. Regardless of which option you take, you're going to end up with the same products. So yeah, it really doesn't matter. So let's say we swap the cations for each other, potassium for iron. I'm going to end up with iron and hydroxide. Okay, now once again we have to build the formula based on the charges. Okay, so I've got a positive 3 iron and a negative 1 hydroxide. So I need 3 hydroxides paired up with the iron, just like I needed 3 nitrates paired up with the iron, right? Because the hydroxide and the nitrate both have a negative 1 charge. Okay, I don't know what state of matter this is, so I'm going to leave this blank. I don't know if it's aqueous, I don't know if it's solid. I'm going to have to look that up using the solubility rules on page 134 in your book, table 4.1. Okay, so I'll look that up in just a second. The other formula is going to be potassium with nitrate, positive 1, negative 1. So this is just a 1-to-1 ratio here, 1 potassium, 1 nitrate. Once again, I don't know if this is aqueous or solid, or I don't know. I have to look this up. Now, before I do that, I want to make sure that my equation is balanced really quickly. Okay, so definitely unbalanced at the current moment. I have 3 hydroxides here compared to just 1, and I have 3 nitrates here compared to just 1. So I think the way that this is going to work is putting a 3 here. Okay, so 3 hydroxides. That's going to give me 3 potassiums as well. So look at this, 3 potassiums, 3 nitrates. Put a 3 there. I think we're good to go. Okay? So 3, 1, 1, 3 are the coefficients. Now, in order to determine these states of matter here, solid or aqueous, I have to consult, like I said, page 134, the solubility rules. Rule number 1 says that most nitrate salts are soluble. Rule number 2 says most salts containing the alkali metal ions, such as potassium, are also soluble. This is going to be a soluble compound, for sure, okay, due to rules number 1 and 2. Now, this one, iron hydroxide, let's take a look. Rule number 5, most hydroxides are only slightly soluble. The important soluble hydroxides are sodium and potassium hydroxide. Okay, so this one over here was soluble. It does not say anything about iron. So this is only slightly soluble. And as we discussed in class, slightly soluble essentially means that it's going to be insoluble. Okay, it's going to be a solid. It's not going to be soluble enough in water for us to consider it an aqueous solution. This is going to be your precipitate. Okay? All right. So this is our fully balanced molecular or formula equation, okay? Now what we need to do is we need to come up with what is called the complete ionic equation, okay? Let me type that out here. So complete ionic equation. All right, this is where we are going to break up every aqueous compound into its constituent ions, okay? Every aqueous ion, or every aqueous compound, we are going to break it up into its constituent ions. Okay? The solid compound, we are not. Okay? The reason we're doing this is because these aqueous compounds don't actually exist as compounds. They exist as free-floating ions. They're dissolved. Okay? All the ions are dissolved in water. They're dissociated from one another. So here's what I've got. I've got 3 potassiums. These potassium ions each have a positive 1 charge. And I have 3 hydroxides. Oh, sorry. Let me be very careful here. These are aqueous. So each one of these individual ions needs to have its own label. Okay, so I have 3 aqueous potassium ions, and then I have 3 aqueous hydroxide ions. So in the complete ionic equation, when you are breaking up these aqueous compounds into their constituent ions, you need the charges, okay? Because they're no longer in the compound. Here, guys, they're not really in the compound there either, okay? The complete ionic equation is sort of a better representation of what's really going on, all right? Let's see. All right, the next compound here then, iron nitrate. Okay, I don't have a coefficient out front here, okay, or, well, I do, it's just the number 1, right? So I have 1 iron. Iron is positive 3. This is aqueous. And I have 3 nitrates, okay? Now, if I did have a coefficient out here, say a 2 or a 3, I would have to multiply that coefficient by this number here to give me the total number of nitrates. So if there was a 3 out front here, that would be 9 nitrates, okay? But I kind of lucked out. The coefficient here is just 1, so this is just 3 total nitrates, okay? Okay, on my product side, like I said, I am not going to break the solid compound up into its ions. This is a solid compound. These ions are stuck together, so this really is a compound. So I'm just going to rewrite this as is. But then this compound here, I'm going to need to break up into its ions. So I have 3 aqueous potassiums. So we need the charges here. And I have 3 aqueous nitrates. Barely squeeze this in here. Okay. This is the complete ionic equation. Okay. It should also be balanced. Okay. 3 potassiums, 3 potassiums. 3 hydroxides, 3 hydroxides, right? OH3. 1 iron, 3 nitrates, 3 nitrates. Okay? Very good. Now, to get to the final step, which is the net ionic equation, what we're going to do is we are going to eliminate all of the spectator ions. Okay? So the spectator ions are the ions that are present on both sides of the equation as free-floating aqueous ions. Okay? You can think of it like a math equation. If you have x on both sides, then it like cancels out, right? Assuming it's all multiplied, right? So you can sort of cancel things out that show up on both sides of the equation. So look at this. I have 3 potassium ions here and 3 potassium ions here. Same state of matter, aqueous and aqueous. The potassium is not undergoing any sort of chemical change. It's not really doing anything, okay? It's present here, it's present there. It's not undergoing any sort of chemical change. The only thing we want to see in the net ionic equation is things that are actually undergoing a chemical change. So potassium is not. Neither is nitrate. Okay, same thing is happening with nitrate here. It's present on both sides of the equation in the same state. It's aqueous, floating around in the water. So this is also a spectator ion. Okay. Now, the iron and the hydroxides, these are going from free-floating, separate aqueous ions. Now they're in separate containers, right? Because we had a container of potassium hydroxide and a container of iron 3 nitrate. But when you mix those together, okay, that's what this arrow represents, right, is mixing them together. The product of that mixing, that reaction, is the formation of this insoluble iron hydroxide compound. So the iron and hydroxide ions, when they run into each other, when the solutions are mixed, when they run into each other, they're going to stick together in that insoluble compound and fall out as a solid precipitate. Okay? So that is your net ionic equation. It's 3 hydroxides that are aqueous coming from container number 1 plus the single iron 3 or iron plus 3 ion aqueous coming from container number 2. When they're mixed together, we end up with a new compound, a new substance, iron 3 hydroxide, okay, which is a solid. Okay, this is your net ionic equation. Okay, your net ionic equation should always illustrate a chemical change, okay, and should never include these spectator ions. Okay, so hopefully that clears up some things for you guys. Hopefully this helps. I'm also going to be posting a link to a different video, one that I am not producing, which goes over how to come up with these formulas in the first place. Okay, I know some people said they were having some trouble coming up with these formulas, so I'm going to post a link to that as well. Okay, thanks a lot, and I will see you guys next time.